Alright, so welcome to today's lesson on quartics and higher powers and other polynomial functions. So we're going to sort of generalize what we've been doing today into everything above 4 powers. And we've already been working on it in the Kahoots at the end of each class. So I'm confident that we can get this ideas across. Right, so I've got up on the screen here a Desmos screen, and I've got basically, if you read the right hand side, I've got a equals 2. A is the power of x, so I've got a parabola here, which is what you can see, this red graph. All right, but I'm also going to increase a by even powers, and we're going to have a look at what we see. All right, so if I increase a to the next one, which is 4, you'll see it sort of gets a bit of a square bottom, but it still looks vaguely parabola-ish. All right, you can see as we go through other even powers, and it's only even powers that I've set the slider to, that it stays parabola-ish. It just becomes decidedly more square at the corners. All right, and as if we increased a all the way out to some obscene number, it would become quite square. Now keep in mind, it still behaves like a parabola, right? So it still has a particular point, which is a turning point, because at this point here, x equals 0, 0 to any power is still 0, which means that that point there is going to be lower than any other point on the graph. So it still has a particular turning point. It just means that the point immediately to the right or the left of the turning point is only minuscule amount higher than it. All right, so it still behaves like a parabola. It just doesn't look exactly like one. You're not going to be able to get that nice curve at the bottom here showing clearly where the turning point is. All right, so keep in mind we want to specifically look at quartics, which is 4th power. You can see it only just flattens off a little bit. What I want you to take away from this, though, is that if that power is an even number, it does behave just like a parabola. All right, so 4th power looks like this, okay? And we can use the same information that we use with quadratics to do the same sorts of things. So an example question might look like this, where we're being asked to sketch I'll just move this out the way. I don't know how to move this out the way. There we go. All right, so sketch this graph. All right, so we've got our axes. We know it's a quartic because the highest power is 4. We know it's in turning point form because of the way it's written. So I can read this out. This is my h value. This is my k value. So the turning point is at positive 2, minus 1. So let's say 1, 2, there's minus 1. Put 3, 4, 5 on there as well. All right, so other important information is that I need to know the y-intercept. So the y-intercept is calculated as normal. So the y-intercept is when x equals 0. So I'd have 0 minus 2 to the power of 4 minus 1. 0 minus 2 is minus 2 to the power of 4 minus 1. Minus 2 to the power of 4 is 16, positive 16, because of the 4th power cancels out all the negatives. 16 minus 1 is 15. So my y-intercept, let's call it up here, is 15. All right. X-intercept calculated the same way as per usual. So 0 equals x minus 2 to the power of 4 minus 1. Minus 1 equals x to the power of 2 minus 4. No, sorry, not minus 1. That has to be a positive one, doesn't it? Otherwise it wouldn't have a x-intercept. So then the quartic root of 1 is equal to x minus 2. And we should also plus or minus because there's 2 solutions being the 4th power. The quartic root of 1 is just 1. So I have, when I move that 2 across, it becomes 2 plus 1 or 2 minus 1, which makes sense with what we know as the turning point. The turning point is at x equals 2, so it'll go 1 either side of that value. So I plot those on. And then I'm going to join them up, but I'm going to make extra care not to make it look like a parabola. I'm going to flatten off the bottom a little bit more than I would normally, and I'm not going to try and I have to try and hit 15 up there. Pretty messy, and the bottom doesn't even look flatter than it normally would, so I'm going to erase it and try again. All right, my scale has not allowed me to work the way I would. I've drawn it a bit too small. All right, so something like that would be a nice drawing of a quartic with the points labelled. All right, and the turning point at least given some way to show. All right, then you might label it like so, making sure to put arrows on your graph, on your end of your graph, so that you know it keeps going unless this function has a domain attached to it, which this one doesn't. All right, so key takeaway here is that we can treat quartics exactly the same as we do parabolas. All right, so let's have a look at a few others. We're going to solve each of the following equations for x. Now remember, solving is finding the x-intercepts, but we don't have to sketch these, we just have to solve for the x-intercepts. So first step is that you would factorize each of them. So let's have a look at A. We've got x to the power of 4 minus 8x. All right, so I'm going to say that in each term there is a common factor of x, so I'll factorize that out. I end up with these two factors. All right, so null factor law says that either x equals 0 or x cubed minus 8 equals 0. Now don't be tempted to assume that this factor is a point of inflection factor. A point of inflection factor, as we saw in cubics, only occurs when the factor would look like this, where it's cubed outside the brackets instead of inside the brackets. As you'll see when we solve this, it will actually solve into just one solution. All right, so x cubed equals 8, cube root both sides, x equals the cube root of 8, which we might know is 2. So there are only two solutions here, x equals 0 or x equals 2. All right, so this quartic only has two x-intercepts. So when you come to graph them, you'd be using that to help you. Having a look at B, we've got 2x to the power of 4 minus 8x squared equals 0. So again, looking for common factors, you'll notice that it has each term has a 2 as a common factor and also an x squared as a common factor. So 2x squared being my common factor, I'll divide it out and I end up with x squared minus 4 equals 0. So null factor law says that either 2x squared equals 0, which gives us x equals 0, or x squared minus 4 equals 0, which should give us x equals plus or minus 2. All right, so this one has three x-intercepts, 0, plus 2, and minus 2. All right, so we're starting to see here different scenarios play out, which we saw in the Cahoots last week, where quartics can have up to 4 intercepts. Not D, that should be B. C, sorry. All right, so this last one, x to the power of 4 minus 2x cubed minus 24x squared equals 0. Now again, to factorize it, you might notice that I'm not always using my factor theorem, remainder theorem. If I can factorize this by sight without going to that, I can do that. All right, so I notice that in here there's a common factor of x squared in every term. So if I factorize out x squared, I'll end up with x squared minus 2x minus 24 equals 0. And I notice then that this is a nice quadratic. So x squared, and this will give me x minus 6 and x plus 4 equals 0. So I've got three solutions here, either x equals 0 or positive 6 or negative 4. All right, so when you're doing quartics, just like cubics, we need to find the turning point, find the x-intercepts, find the y-intercept, and we can do that using each of the methods we've learnt previously. We just have to apply it to a slightly higher powered polynomial. All right, now going back to the Desmos screen, you'll notice that I had other entry lines underneath the first one. This is a similar scenario, x to the power of b, which is starting out as a cubic, all right, x to the power of b, and I've set this one to go up by odd powers. And the reason I've set this to go up by odd powers is I want to show you the pattern, all right? So it starts with x equals 3, which is a cubic, x cubed, and it's going to go up to 5, 7, 9, and so on. And watch what happens to the shape of the graph. Again, you can see it maintains that same shape, just gets squarer at the corners. So the same behavior is shown here as what happened when quartics were introduced. The same base shape of parabola is there. The same base shape of cubic is there, just gets squarer at the corners. All right, and then if I go one step further and now show you x to the power of c, where c could be any whole number, watch what happens. So this is, we start with a parabola, we move to a cubic, we go back to a quartic, cubic shape, parabola shape, cubic shape, parabola shape, cubic shape, parabola shape, and so on, with each progressive step making the corners squarer. All right, so this is a really important lesson. We know now that doing that doesn't change much about the polynomial. It just changes how many x-intercepts, how many turning points, and so on that you'd be looking for. All right, so all our skills stay the same. All that changes is how we apply them and what polynomial we're doing it to. All right, now to finish off a few lessons, we're going to have a look quickly at odd and even functions, which there's a specific reason we bring it in here, because it kind of can make it easier for you to sketch graphs if you know if a function is odd or even. All right, so the textbook definition is that a function f is even if the graph is symmetric with respect to the y-axis. All right, algebraically, f is even if and only if f negative x equals fx for all of x. A function is odd if the graph is symmetric with respect to the origin. It's odd only if f to the f of negative x equals negative f of x. All right, and I'll show you some pictures so that you can sort of visualize what it means here. All right, so the first one, we've got even functions. This is an example of an even function. All right, so you will see here that this is even because it is symmetric about the y-axis. So this point here is the same as that point there. All right, this input yields the same y value as does the opposite of the same input. And that's why they use this terminology here. F of negative x is equal to f of x. So whatever this input is, it's the same as the opposite. All right, so the output for this input is the same as the output for the opposite of that input. All right, I'll give you some examples. This is a parabola. So let's say that the equation is x squared plus 2. So we might say that when I plug in, I'll just make that function notation. When I plug in f at 1, I get 1 squared plus 2, which is 3. If I plug in f at minus 1, I get minus 1 squared plus 2, which is also equal to 3. All right, so you can see here that it doesn't really matter if that input is a negative. Because it's inside the brackets, the square will get rid of the negative, and therefore the output will be the same on either side of the y-axis. All right, this is an example of an even function. Okay, I hope you notice that if we had a parabola that looked like this parabola is no longer symmetrical about the y-axis. It is symmetrical about its own axis of symmetry, but not this y-axis, which means that this is not even. All right, so only functions that are symmetrical about the y-axis are even. Okay, so lock that away, and now I'll show you what odd functions are. So an example of an odd function is this. All right, now this one is slightly different. It's not symmetrical about the x-axis, which you might think because even was symmetrical about the y-axis. A function is odd if the graph is symmetrical with respect to the origin. Now that is a bit strange because the origin doesn't normally feature in our graphs. Right? What this means is if I was to rotate this blue function 180 degrees, then the function would become the same. All right, so I'm using the origin as a rotational point and I get the same function. It is not a mirror point like in even functions, it is a rotation. All right, so odd functions are rotations. All right, and they have this special property where when you plug in an input, you get, so if I plug in x, I get this output right here. That output is the same but negative or positive as the input, as the output when I plug in the opposite of that input. So let's say that this function here is f of x equals x cubed. If I plug in f at 2, I get 2 cubed, which is 8. If I plug in f at minus 2, I get minus 2 cubed, which is minus 8. So you can see it's the same but opposite, right? As the input was the same but opposite, which is very different from this even function over here. All right. Now the notation they used to show this was that the input f of x, erase that. The input f of negative x is equal to the opposite of the entire output. All right, so let's put that into terms of what we just did here. F at minus 2 was the same as the opposite of the output, the opposite of the output for f at 2. Now let's go a little bit further. F at minus 2, the output was minus 8. If I chuck a minus sign in front of the output for 2, I get minus 8. So you can see there that minus 8 is the same as minus 8. So what they're trying to say here is, if you can put a negative sign in front of the entire output of an odd function and have it be the same as the output for a negative input, then the function is completely odd altogether. All right, and this will make a little bit more sense when we do a few examples. All right, so let's have a look. It says state whether each of the following polynomials is odd or even. So I've got f of x equals 6x to the power of 4 minus 3x squared. Now all I have to do this is to use my algebraic rules here. That was to show even, and the other one was f at minus x equals the opposite of f at x, which is to show odd. All right, so I don't need to do any special work. I don't need to graph them or anything like that. This is the easiest way to do it. I just plug in minus x into this input here because I already know what f of x equals. It equals that. All right, so f at minus x is going to be 6 minus x to the power of 4 minus 3 minus x to the power of 2. And that's going to get me 6x to the power of 4 because negative will cancel out with an even power minus 3x squared. So now question, has this changed from the initial? No, it hasn't. We can see here that that is the same as this, which means that this case has been met, which means the entire function is even. All right, because the output for negative x was the same as the output for x. All right, next example, gx equals 3x to the power of 5 minus x cubed plus x. All right, again, we'll have a look at whether it's odd or even. A clue for you, I would suggest, is that you start thinking in terms of the power, looking at the lead power. If the lead power is an odd power, I'd suggest that the function can't be even. All right, so let's try substituting in negative x, which equals 3 negative x to the power of 5 minus negative x to the power of 3 plus negative x, which is going to equal minus 3x to the power of 5 plus x cubed minus x. Now, we notice that this is different from the initial, but this was always going to be different because the rule says that the output for negative inputs is going to be the opposite of the whole thing. So quick and easy check is to chuck a negative sign in front of every term in the initial one, which will change it to become, and now you start to see that it's the same as that. So therefore this function is odd because this output is the same as the opposite of the initial output, which is what this says. The output for a negative input is the same as the opposite of the positive output. All right, I'm not going to go through the other two examples because I don't think we need to. What you need to do, you need to remember is if there's a odd or an even power, you need to start thinking in terms of, is this symmetrical or is it able to be rotated about the x-axis or the origin? Just like for the quadratics, there was an example that showed if you shift a quadratic sideways, it doesn't become even anymore. Same thing for a cubic. If you shift a cubic up, notice now that if you rotated this about the origin, it wouldn't be the same thing. The output for this x value is way higher than the output for this x value. All right, so if I rotate this around, this one is going to be lower than that one. So it's no longer an even function. All right, so it's not a rule that's true every single time. It's only true some of the time. All right, you just have to evaluate each function on a case-by-case scenario to assess whether or not it's even or odd. To finish off this part, there's a few properties for all even degrees and all odd degrees. All right, so we notice that for even powered functions, the negative input was the same as the positive output. F at 0 is always 0 because 0 to the power of anything is 0. And as x approaches infinity, y2 also approaches infinity. Right? That makes sense because as we have a parabola or a square thing look like this, as x get bigger, y also increases that way and that way. All right. This stuff here, don't stress too much about that for now. It will make more sense as you actually graph some more of the functions. All right. So for odd powered functions, odd degree functions, the output for a negative input is the same as the opposite of the output for all of x. All right, which we just saw in this example here. F at 0 is still 0 because 0 to the power of anything is 0. But as x approaches infinity, y approaches infinity. As x approaches negative infinity, y approaches negative infinity, which makes sense because we know that as x gets bigger that way, y increases up there for a cubic. As x gets bigger to the left, y gets bigger going down. All right, so that makes sense. We already know that. This is just written in notation that might look a little bit different. And again, these will make sense as you come to do examples with them. All right, to finish off, we've got a good thing to do now. We're not doing any learning. We're just going to apply it into a worked example. So we've been asked to sketch on one set of axes two graphs. Excuse my poor x-axis. That's terrible. There and there. We've got f of x equals x to the power of 4 and g of x equals 2x cubed. So obviously one of them is going to look like a parabola with a flat bottom going like this. The other one is going to look like a cubic going like, it's going to be, what is it, 2 has dilated it. So it's going to go across, start down here, go up here, and then cut outside like that. All right. So it says solve the equation f of x equals gx. So this is a simultaneous equation. You can do this on your CAS by solving the intersection point, but to do it by hand, you just go x to the power of 4 equals 2x cubed. Set the two equations equal to each other. This will give us x to the power of 4 minus 2x cubed equals 0. Factorize both terms and you get x minus 2 equals 0. So now I know that there is x cubed equals 0, or x minus 2 equals 0. So this gives me x equals 0, or x equals 2. So the intersection points are here, which we knew, the point of inflection and the turning point are the same spot, or x equals 2, which is here. So I'll label that. This is 0, that's 2. All right, so it says to solve the equation, which we've just done. I've got x equals 0 or x equals 2. Then it says to solve the inequality. F of x is less than or equal to gx. Now this is where notation is all important. All right, so we are looking for the part where the f of x, which is the red one, the red is less than the blue. All right, so you can see here that the red one is less than the blue in that section there. All right, and this is what the previous question has asked us to do. It's asked us to find the intersection points, and you can see here that the red is less than the blue nicely between the two intersection points. So we can say that f of x is less than or equal to gx for the interval 0 to 2 inclusive. All right, because it said or equal to. It didn't say just less than. All right, this is where you need to pay close attention. If this question had been fx is less than gx, then you would have had your answer looking like that, because at that point the two graphs are equal, given that they intersect there. All right, so what we're going to be looking at now is graphing two sets of equations, solving them, and finding intersections between them, just like we did for inequalities with cubics and quartics previously. Sorry it's been a long video, but there's quite a bit of technical information that we had to go through. So to just recap, remember that we can treat quartics the same as parabolas. They can be in turning point form or factored form. If they're written in turning point form, the h and k values are still relevant. Remember that they just look like a sort of flattened bottom parabola. We can still factorize each of them the same way. There's no change in the skills there. Then we looked at odd and even functions, where odd functions are symmetrical around the y-axis, so treating it like a mirror, and even functions are symmetrical about the origin, so treating it like a rotational axis. All right, there's a few rules to look at, or a few properties to remember for odd and even functions. These are the same for all even functions and all odd functions. All right, and then we came to look at sketching, graphing, and using inequalities on two different graphs, which we hadn't done very much previously. So to cap it all off, we've got this particularly useful thing from the book, the key concepts for the set. All right, so it just goes through a few little points. Quartic turning point has the same shape as that, but translated. The implied domain of all quartic functions is R, just like for parabolas. A function is even if this criteria is met, symmetric about the y-axis. Odd if this criteria is met, rotational symmetry with respect to the origin. And a power function is a function f with a rule like this, where R is a non-zero real number. All right, so the common ones we deal with in this book are -2, -1, half, third, and then positive integers. All right, we don't go into any super duper fancy ones, so we've already done a lot of those, and you'll come to practice more with them as you go through the rest of the year.